So welcome all, and to the new part of the course, which deals with deep learning methods. Now, till now, we have been dealing with methods like linear regression, logistic regressions, and variants thereof. These methods are methods which sometimes you may question, what does this have to do with deep learning? Because essentially we could have done this without having discussed anything connected with machine learning. But as you've seen, linear regression allows us to have a very simple direct link with the parameters, the unknown parameters. So we say we train the parameters by inverting a matrix. So that's ordinary least squares and ridge regression. In lasso regression, as you saw last week, you can actually code lasso by using gradient descent. So gradient descent, or the family of gradient descent methods, is what we will have to live with. So the case of linear regression with ordinary least squares and ridge regressions, these are the kind of dreams of an easy past. Now we have to deal with a gradient descent implementation. And this is actually the first part in project number 2, where you implement different gradient descent solvers. And we will start discussing that during the lab sessions. And today, we will see how we can set up our own code for a simple neural network, a very simple one, where we simply take scalar inputs and have scalar outputs. And then we are going to expand upon that to a matrix as an input, which could be the design matrix, and an output which doesn't need to be a scalar, but can be a vector or a matrix. And we're going to introduce the different parameters. Now, Rashka's chapter 11 is the one which gives you a lot of information on actually how to develop the codes, but there are lots of codes examples in the notes here which you can follow. So the idea is actually we build from scratch our own code, but you can use the codes for gradient descent and obviously automatic differentiation, which we are going to discuss today as well. Now, the material for the active learning session, and this is actually a session where we are going to start. So the exercise this week is about you implementing a gradient descent solver. And that means that there are different methods which we need to implement. And exercise 1, or the exercise this week, simply deals with that. So take a look at the material from last week and also from the week before, especially the one on stochastic gradient descent, because that's what we end up implementing at the end. Okay? So this is just a little bit about messages and the kind of plans for the week. And as I said, today, we are simply going to look at the structure of a neural network. Now, we will mainly deal with something which is called either artificial neural networks or just plainly neural networks. So this is going to be the focus of project number 2. Then, after we've done with that, we are going to implement, so you can read this, I'm not going to read everything here. So we will deal with something which is called a feed-forward neural network. And that has a famous algorithm which allows for the training of the unknown parameters. That algorithm is called the backpropagation algorithm. Now, as you will see later today, backpropagation is nothing but automatic differentiation in reverse mode. And I will try to motivate why the reverse mode is better than what we last week loosely mentioned as the forward mode. So backpropagation is, in essence, you applying the chain rule for differentiation. And you can, when you have a function which depends on many variables, you can decide whether you start at the endpoint and then trace back to the input, or you go from the input to the endpoint. Now, one of the reasons for why neural networks normally use the backpropagation is simply because you often have fewer variables at the endpoint, which means that you often start with a scalar, or you can start with a vector of low dimensionality. Your input, on the other hand, can be a complex design matrix with many variables. So this is something which in general saves some CPU cycles. And it also allows for an easier decoding of the codes in case something goes wrong. And it also allows for a slightly more efficient calculation of derivatives. So backpropagation is the central piece in a feed-forward neural network. So what does a feed-forward mean? You initialize your parameters, which you are going to optimize, like you did with the beta parameters in linear regression. You initialize them with random values, and then you feed everything through the network, and you produce an output. This output is compared with the target value. Then you take the derivative of your cost function, and then you propagate backwards the different gradients till you reach the input layer. And when you've reached the input layer, then you have new values for the parameters, and then you make a new feed-forward pass, and then you go back and forth. So one iteration contains a feed-forward pass where you construct a new output, then you train the parameters, and you go backwards, and then you have new values for the parameters, and you go back and forth till this cost function, which we have, doesn't change by more than some input or some variables which you selected to be a small number. Okay, so this is the overarching philosophy. Now, feed-forward neural networks are data greedy. And it means that they normally, the standard way they are set up, you deal with all the data you have. You don't make any attempt to reduce the dimensionality of the problem. Now, this means that we need to think of ways of reducing the dimensionality. And after we've done with neural networks, we are going to discuss convolutional neural networks, which are widely used for image recognition. So the basic idea of convolutional neural networks is that you take your input data, and then you have a filter which reflects your insight about the data. So if you think of an image of a house and you're training a model on recognizing houses, you don't take all pixels in an image because many of the pixels are just the walls. And that's pretty boring, right? And the walls have normally, if you have painted and maintained your house regularly, it's just one color. So what you would feed into the network would be where the corners are, where the windows are, where the doors are, and where the roof is. So that means that you can filter away a lot of information. So that's a filter. And convolutional neural networks are often represented by the applications of many such filters. And then you scale down your image. You scale it down, and when you scale it down, you do the training. So that's a typical example of how you can reduce the dimensionality of a big problem. So in imaging, and we do actually have a course which runs in the spring, which is called Machine Learning for Imaging at the Department for Computer Science. And that simply focuses on convolutional neural networks and methods to recognize images. Okay, so that's one of the next topic. And then after that, we are going to discuss, and in that case, we are mainly going to present how you can implement these methods. So you're not going to write a convolutional neural network. You're not going to write a code for recurrent neural network, but we will use libraries like PyTorch or TensorFlow. And that's the standard approach which we will typically take for project number 3 if you want to use these methods. Okay? Any questions about this kind of more overarching view? Now, one of the things which you should also keep in mind is that many of the advanced methods, they often use a neural network. What you are going to do in project number 2 as an input to the model itself. So in convolutional neural networks, there will always be a neural network which does the final training. If you do a recurrent neural network, which is extremely useful if you have time series, which is pretty common if you make measurements of some events. Suppose you measure the pulse of a patient every 10 minutes, then you will have a time series of how the pulse varies depending on different inputs. So you can see how the pulse of a patient varies if that patient is exposed to some kind of external probe. So recurrent neural networks are extremely useful for time series, and they're widely used also in language models. So it's actually recurrent neural networks are often the basis for large language models. And we will scratch the surface, but we will show you how you can use the libraries like TensorFlow and PyTorch. And then we are going to have an application of neural networks. So the code which you develop in Project 2, you can use that one to solve differential equations. And that's a very hot type of applications of deep learning methods. Now, these are the basic deep learning methods, which we will discuss through the semester. Now, we do have advanced courses at the university, so if you're interested, please let me know, and I can point you to the more advanced courses. Like we have one which is called Physics 5429, where people can choose different types of projects, and we've had people who write their own convolutional neural network code, their own large language model, etc., etc. So we wanted just to give you the kind of flexibility which you can see when you start with a method like a neural network. So neural network is actually fundamental in many of these methods as a kind of basic method which enters many of the other ones. So something which we will not discuss are things like autoencoders, which essentially reuse a code for neural networks in this basic formulation. We are not going to look at variational autoencoders, etc., but we are going to give you the basics. And if you understood the basics of a neural network, you actually have much of the basics of deep learning methods. Okay? Any more questions? So this is just a little bit about how to say generalities and some kind of overarching motivation. And we are going to look at something which are called multi-layer perceptrons. And the way we can think of this, and I'm going to repeat this in the notes, on the whiteboard notes a little bit later, but now I just want to give you a kind of overarching picture. So if you think of, so historically, much of what you see here has been inspired by neuroscience. And that's why you will find names like neurons. I'm often going to call this for nodes or units, but sometimes I also use neurons or perceptrons. So a perceptron is actually a very simple model of how a neuron fires a signal. So you're sending in some inputs. These inputs get weighted by some constants, W1, W2, etc. And then this is fed into a function like the sigmoid function we discussed in connection with logistic regression, which then modulates the result. And then this spits out an output Y here, which then could be something you have decided that if it's less than 0.5, you spit out 0. If it's larger than 0.5, you spit out 1. Or you just send out that value F if you're doing a linear regression problem. If you have a typical classification problem where you have binary results, this Y of I you see there is something which is normally just a discrete number like 0, 1, or it could be the class of handwritten numbers from 0 to 9, etc., etc. Okay? So this is the kind of graphical way which we are going to use. So when you look at many of the ways we represent this neural network machinery, it's often done in such a graphical framework. Now, the neural network, a typical one, is something which contains so-called hidden layers. And every layer here consists of a number of neurons. Now, what you see here is something which I'm going to put down in words a little bit later. So I'm going to use these slides a little bit in the beginning. Now, what you see here is now your model. When you did linear regression, your model could be a polynomial. Your model now contains the number of hidden layers, the number of neurons. It contains also these functions F, which you can play around with. And we will come back to what kind of functions F we are going to look at. So these functions F are normally called activation functions. And one of those which you have encountered is the sigmoid. which you then can use to output either 0 or 1, or you can just feed forward the value which it produces. And then there is finally an output layer, which produces the output of your model. So what you have to think of now is that your model is the architecture of the network. So it's no longer like a polynomial or some kind of Fourier series, if you are familiar with that, but it's actually the architecture of a network. That is your model now. So this means the following. If you think of what you did in project number 1, where you have a design matrix, which represents a polynomial, that is your model. Now, for a neural network, you don't feed in a design matrix in terms of a polynomial, because then the network will actually try, you can do it, but then the network will try to fit a polynomial of a certain degree. But it does not need to mean that your data, x and y, represent a polynomial of, let's say, degree 5. Your data could be a much more complex object. So a neural network, in its ideal way, since there's something which is called the universal approximation theorem, which states that you can approximate a continuous function to a specific error with just one hidden layer. And this function can be a nonlinear function. So that means that if you just feed in x and your output, then the network should be able to find the best possible representation of the function. So this is a common error we often do, is that we take project 1, we set up the design matrix, which we have struggled with setting up for the Franke function, as an example. And then we want to reuse it, but then we are feeding in a function which we have parameterized, which we have modeled. Whereas the network is the one which should be able to find the optimal parameters for you, with just the input and the output as information. So just keep in mind of that small difference. You can always train a neural network with a design matrix as you did in project 1, but then you're forcing the network to fit a polynomial of a certain degree. Okay? So I'm going to skip some of these examples. I will come back to these. So I'm going to scroll down a little bit. But what I wanted to say a little bit about, which is somewhat more interesting for us, is the mathematics of deep learning. Now, if you're interested in these topics, there are actually 2 new articles which you can download. So if you want to dig a little bit deeper into the mathematics, then you can take a look at the 2 first references. And then when we build up the code, this chapter 11 of Rashka et al. Is extremely useful, because that also has examples where you can, how you build up your own code. And then later, it also shows you how you can do that with PyTorch. So take a look at this material when you are developing your own codes. Now, so one of the things which we have to, which we are going to do now, is to introduce the basics of a network. So we are going to look at input and output layers, and we are going to have hidden layers, which we will label with a letter little l. And each one of these has a set of parameters. So now I'm going to use this Greek theta, uppercase theta, as a collective container of the parameters of the network. So previously we had the parameters beta. Now I'm going to use W for what's called the weights and B for something which is called the bias. And later when we are going to make a simple model, you will see that this bias can be interpreted as the intercept in your polynomial fit. But in general, now we are going to use theta as a common denominator for the unknown parameters we want to optimize. And there is a, if you take an overarching view of the network, this is the architecture. As you can see, as I mentioned previously, there is an input and an output layer, where the input layer is defined by the inputs X, or your design matrix. And the output layer produces the model output, which is then compared with a target value Y. So you will have a target value, and you have some kind of output of your model, which is a network, there's going to be a given number of hidden layers and neurons or nodes or units for each layer, and this can vary. So these become parameters. So when you come to deep learning and neural networks in general, welcome to the jungle of parameters. And when you now are going to look at, let's say, the bias-variance trade-off, you can play around with the number of nodes and the number of hidden layers, because that will represent the complexity of your model. Then we are going to have activation functions. And these functions are essential. And you will see that people will play around with different types of activation functions. So one thing we want them to be is to often have analytical expressions, because that makes the computations easier. We want to have derivatives which are hopefully not discontinuous and well behaved and have nice analytical expressions. So we are coming back to the types of activation functions, because you will play around with that in project number 2. So that becomes a new parameter. And then you may ask, which one should I use? So there is a problem, since we are calculating gradients, and we are going to calculate the derivatives of this activation function. If this activation function has a derivative which vanishes, then the training stops. And that's called the vanishing gradient problem. And that is a problem which actually almost killed the whole field before people understood what was going on numerically. And then we also have exploding gradient, and we have techniques like clipping gradients, which means that if the gradient becomes too big, we just put it back to a smaller value. And you will see that there's a lot of ad hoc implementations of such algorithms in neural networks calculations and deep learning calculations. And then you have the last layer, which is called normally the output layer, and that has normally an activation function which is different from the hidden layers, because that depends on the type of output. So if you do linear regression, the output is not modulated. It just spits out what it produces. If you're dealing with a classification, you would like to spit out 0, 1, if you have a binary case, or if you have many cases, let's say the 100 numbers, then it would like to spit out the probability for the different numbers. And then finally, what you end up with is also to define a cost function, or loss function, as we often sloppily call it. And these 5 points which you see there are the points which we are now going to play around with. And these constitute the architecture. So if you study the bias-variance trade-off, the bias-variance trade-off will then depend on the way you design the model, which is the architecture of the neural network. So I'm just trying to keep this kind of more overarching view first, so that you see, hopefully see the wood for the trees. And then we have the optimization problem. And the optimization problem is essentially us if you take the mean squared error, which you've seen many times. So instead of beta now, I have theta. So I'm just replacing it because we are going to add more parameters. And then this beta is something which we can reserve just a plain polynomial fit here. So if we scroll down here, there are more things which make life messy, really messy. And that's the different gradient methods, because in this case, we don't have analytical nice expressions for the unknown parameters, which means that we need to play around with different gradient descent methods. So one thing is actually to have a gradient descent with momentum. That's a standard kind of default approach. Now then, as we discussed last week, it's common to do a stochastic gradient descent. And stochastic simply because you often don't want to be stuck in a local minimum. And you want to also compute the gradients more efficiently. So stochastic gradient descent and these various families of learning rate approximations is actually something we have to implement in project number 2. Here, you can take the codes which we have. And in that case, it means that you would try adaptive gradient descent, there's actually a typo here. Adapt is there's an A too much. Root mean square propagation, and then ADAM, adaptive gradient with momentum, and many other. Now, there's one thing I wanted to say before we go into the whiteboard, and that's about the universal approximation theorem. And that simply says, if you now look at your function, you have a deterministic function as before, and you make a model, which is your neural network, which now depends on these parameters theta. Then what it says is that you can approximate such a function f of x with a neural network which at least, and if this is a non-linear function, that means beyond linear, then we can approximate it with a neural network which has at least one hidden layer. It doesn't say how many nodes the hidden layer needs. So the proof of this theorem, which was presented by Sybenko in '89, is similar to what some of you may have encountered when you look at the convergence of a polynomial approximation, because there you have something which is called the Stone-Weierstrass theorem. And this is something which you actually have played around with. And this approximation theorem simply states, and this was extended by Hornig in '91, is that you can, by letting any non-constant bounded activation function to be included, because the proof by Sybenko was done with the sigmoid function, whereas Hornig actually extended this to non-constant bounded activation function. And that means that what you can prove then is that the expectation value squared of the function and the model which you have said is smaller than this integral, if you know this probability, and this is smaller than an epsilon, which you have to fix. So none of the proofs give any insight into the relation between the number of hidden layers and nodes and the approximation error epsilon. It only says that you can approximate the function to a specific error, but it doesn't say how big that one is. So that means that it's left for us practitioners to play around with number of nodes, number of layers, activation functions, etc., to see what kind of error we will accept. Okay, so now what we are going to do now is to set up a neural network. And I'm going to, before we do that, I'm going to come back to some of these, but we are going to break this down into something much simpler. But what I wanted to say something about now is automatic differentiation, because that becomes the algorithm which in a way saves the day for us when it comes to calculations of derivatives. Because we often want to change cost function, we want to change activation functions without having to hard code these quantities again and again. And automatic differentiation is the important thing. So in the slides here, you will find some small reminders about the chain rule. So if you have a function, so take a look at these if you feel a little bit rusty about the chain rule. So if this function, if there is a function which depends on x and y, and x depends on t and y depends on t, then the derivative df dt is simply now given by these derivatives which you see here. And I've left out the unit vectors if you think of this as a vector. So these will be the derivatives if you have a multivariable function where this x does not depend only on t, but also on a variable s, then you would have a df ds, which now has a derivative with respect to x and derivative with respect to y. And then the gradient of this function is now simply given by the product of this vector times this matrix. So this is just a quick reminder. Now, why do I do this? Now, because I wanted to show you what automatic differentiation means to us. And there are two modes, as I said, one which is called reverse mode and one which is called forward mode. Actually, what happened there doesn't have a reverse mode with all the water which went out on the table. Sorry, I couldn't resist. Okay. So let's now switch to the whiteboard here and look at some examples. Yeah, I realize it shut up here because it's I think it's gone here. So I have to speak a little bit louder. Can you hear me if I speak like this? Okay, good. Just a small moment here. We are going to go back. Oops. Sometimes when I have the same problem as last time with the arrow. So let me just go down here. There we are. And now let's share again. So the thing I wanted to discuss with you now is the first thing, which is automatic differentiation, and what that is going to mean for us, and why we are going to implement that one in the codes for a neural network. You will see that that really makes life much, much easier for us. So let's just bring back some basic elements. So this is automatic differentiation. Differentiation. It's a long, difficult word. So let's look at an example. And let's just pick a function f of x squared, which we can rewrite as the exponential of a, where we have defined a equal to x squared. Then if we take the derivative of df of d of x, we know that this should be equal to 2 times x of the exponential of x squared, which we can rewrite as 2 times x times the exponential of a. So this sounds pretty trivial. If we now look at the way we are setting this up, we can set this up as a graph. And this graph is going to be pretty similar to a simple perceptron model. So that means that we can view this now, since these are scalar quantities. So we can have an x here as an input. This feeds in to this function, the exponential, and it produces this variable. So it has a in here, and that produces a new quantity, which is now given by a variable which I'm going to call b. So I'm going to call b for this exponential of a. So we have a mathematical function. This produces b, which then defines the variable f. Okay? Nothing particular here. If you now look at the way you would set up the partial derivatives now, you can set this up in, or the derivative of f. So we want df dx. And this is something we can write out as a df db times db dA and dA dx. Does that sound reasonable? And we know that the df db, since b is equal to f, then that one has to be equal to 1. So another piece of information is that b is equal to f. So that means that the term which you see here, the first one, has to be equal to 1. So let's just change page here and write this again. So if it's okay, I'm going to change page now. And if we do that, what we have is the df, db, and then we have db. So this is just a plain application of the chain rule of dA dx. This is equal to 1. This is obviously equal to the function itself, exponential of a. And this quantity here is just 2 times x, according to the definition which we have used. So that is 2x exponential of a, which is again 2x times the exponential of x squared. Now you can now look at this in 2 different ways. The way you calculate the derivative. So if I take this one first, so I start with f and take the derivative with respect to b, and then I take the derivative with respect to b and a, and then I have the final one. This is normally called reverse mode. In this particular case, there is nothing to be gained by taking the forward mode or the reverse mode. Alternatively, you can look at this in the following way. So we can now take df, db, and then we have db, dA, and dA, dx. And then we can start with the derivative with respect to x. We take the derivative with respect to b and a, and then finally the last one. And this is normally called forward mode because we start, if you go back to the graph, which we made, we start with a value x. I mean, where we have the entry point. So these are just 2 ways by which we can evaluate this set of chain rule derivatives. Now, this example is also a little bit important because when we move to the next example, you will see that there are some kind of small issues which are important to think of. So automatic differentiation is not symbolic derivatives. So in the slides, you will find an example with SymPy. So many of you have used SymPy. So SymPy is a way to get analytical expressions. And there, SymPy, when you ask SymPy to calculate the derivative of that function, it will give you the expression which you have here. That is, it gives you this expression here. And you can ask symbolic Python to translate that into a C++ program, a Fortran program, if you like that, a Julia program, a Python program, etc. But it's going to be inefficient. So symbolic derivatives are very useful, but are numerically inefficient, and you will see immediately why. So if you go back a little bit now and look at how you would implement this simple, what we might call baby case, okay? So if you now look at the calculations here, if you don't think, the first thing you would do is to calculate x, okay? And then you calculate x squared. So that is one floating point operation. So what we're going to assume now is that all operations are democratically the same, which is not true. It takes more time to evaluate an exponential. But I'm going to call the evaluation of an exponential as one floating point operation. Normally, when you run these calculations, you calculate both the function and the derivative. And you will see that when we are setting up the codes for neural network, this is exactly what we do. So that means if I calculate the function and the derivative, if I don't think, then I have here 2 floating point operations. Then I'm not very smart because SymPy or Mathematica, if I use Mathematica, give me these functions here. Same for expressions. And now you see that if I don't think, I have one multiplication, one floating point operation, a new multiplication that is 2 floating point operations, and that gives me 4 floating point operations for the derivative. And then I have 2 here. That means that I have in total 6. On the other hand, if I pre-calculate this function, the function itself, this one takes the same number of floating point operation, which is 2, but here I can actually save 2 operations. So instead of having 6, which I ended up with, I end up with 4 floating point operations. So that's a saving of operations. Now, let's look at a different example. So let's take an example 2 here. And in this case, we are now looking at the function f of x, which is given by the exponential of x squared plus x squared. So what automatic differentiation does is that it splits your calculations of derivatives in terms of elementary operations. And now you see why we are often interested in having functions like the activation function, which has nice analytical expressions, like the sigmoid function, which is given in terms of simple functions like the exponential. So what we are doing now is to break this down in smaller operations, because this is essentially what automatic differentiation does for it. And we will now define variables, a, which is x squared, and then I define b, which is the exponential of x squared, which is the same as exponential of a, as before. Then I define a new function, which is c, which is a plus b. I have a new function d, which is the square root of c, which is the same as the function f of x. So what we want df d of x, and it's pretty straightforward to calculate the analytical expression. And the analytical expression, the way you would get it from Mathematica or symbolic Python, is going to be like this. And if you translate this into a code, it's going to code exactly what you have here. But you see that you can rewrite this one if you take these different variables as x of 1 plus b divided by d. So if I use Mathematica or symbolic Python, they will give you a code which looks like the analytical expression you get when you take the derivatives. So if I'm calculating this without thinking, and I leave that as a small exercise, this is going to give you 10 floating point operations, which you call flops. And the calculation of this one is going to give us 5 floating point operations. If I don't think, I can reduce this one if I think. So think a little bit, you can reduce that to 4 floating point operations. So the square root is a floating point operation. And you can see that because this will include 1, 2 operations. You have one addition, that is 3. You have x times x, that is 4 operations. And you have a square root, so that is 5 floating point operations. If you pre-calculate, you have to calculate x squared, so that is 1 floating point operation. But then you calculate this one by pre-calculating a, so which means that you have only 1 floating point operation. You have 1 here, plus 1 here, plus the square root, and that gives you 4. Now, when you have done these calculations, and you use this expression, you see now that this expression has 1 addition, 1 multiplication, and 1 division. So you can reduce that one. So this one has actually 3 floating point operations. So when you're calculating the derivatives in a smarter way, you can reduce the number of operations with a factor of 2 in this case, from 15 to 7. Now, when you do automatic differentiation, it is not as simple as this. So life is not that easy. because actually you have to evaluate these derivatives. And there are calls to functions, etc., etc. So after the break, we are simply going to link this with the calculations of the derivatives and the gradients of the cost function as a function of a simple perceptron model, and then later as a function of a simple neural network. And doing this in a kind of baby step fashion is hopefully something which allows you to see how you need to write a neural net, how you're going to write a neural network code. So I'm going through this in a more pedantic way because it takes some time to adjust our minds to the way we calculate the derivatives of the cost function. And now we are going to have many, many more parameters. So instead of just a few, less than 100 parameters, as you've been having till now, we are going to have tens of thousands or millions of parameters. Not in project 2, because that will take a lot of time, but still you're going to have lots of parameters. And then we need to calculate gradients efficiently, and we want to automatize the calculation of gradients in the sense that we want to change activation functions, because that becomes part of the architecture of the network. So these are technicalities which play a major role in the setup of a code for a neural network. Guys, you've been extremely patient this morning here. I don't hear any voice, no objections, no nothing. Should we take a small break? Is there any objection to that? No. Let's do 15 minutes, right? Okay. So before the break, we looked at this example of automatic differentiation. And this example here is complex enough that it should give us a kind of feeling of what happens with automatic differentiation. So let's look at the derivatives which we get and the usage of these functions which we have defined now. So if you look at what we did before the break, we defined these functions from A to D. And when we now calculate the derivatives, we can now, so because what we want is this quantity. So let's quickly look at what these derivatives end up looking. So clearly, this d of a d of x, is something which is going to be equal to just 2 times x. And then I'm going to have, these are the different derivatives which I'm going to need. So that will be given by dB of dA and dA dx. And that is nothing but 2 times x of the exponential of x squared, which is again 2 times x of the exponential of this function a, which we had. When we look at this derivative of c with respect to x, this contains now, if we go back to the definition here, c is actually given by a plus b. So that means that what we get then is dc, dA, dA dx. This quantity is just equal to 1. And this is a quantity which we know already. So dA dx is just times 2x. And then I have plus, and then we get dc dB, which is also equal to 1. And then we have dB, and we need to break that one up in terms of dA dB and dA dx. And this quantity here is nothing but 2 times x of the exponential of x squared. Finally then, if we look at d of d and dc, we need that one as well. We have 1 divided by 2 times square root of c. And then I also know that ddx, which is equal to d of dc times dc of d of x. And this is the same as df of d of x. So this is a way by which we can calculate these derivatives. And if we look at the way we can set up this function in terms of a graph, we can now think of going in the reverse mode or in the forward mode when we calculate derivatives. So if we look at the calculation here, we can now think of this in a graphical way in the following manner. So we calculate a, and this is a function x squared, and then we perform an addition. So there's an operation of addition here, and that leads to c, but what we are adding is the function b. So here we have b, and here we are actually taking the exponential of x squared, and this one leads to a new variable d, which is the square root of c, and this finally ends in the final value of f. So what we want is df dx, and if we bring everything together, what we have then, when everything is collected with these different variables, you see now that we have df of d of x, which is the same as dd of x. We need this function, which we have here, and then we need dc dx, which is this one, and then we have dc dx, which is given in terms of these different derivatives, and then finally db dx, which is this one, is given by this function here. So that means that we can start the calculation of the derivatives. We can start with dA dx, as you have in the curve here, this one, and then we move on to dB dx and dC dx, and then dd dx, or we start here and we move backwards. So when we move backwards, this is called the reverse mode, and this is something which we can actually implement easily in an algorithm. And in the Jupyter notebook for this week, you will see how we can implement this in an efficient way as a code. Now, for this type of problem, we can also replace the functions with a program. So you're not limited to functions of simple or operations on simple functions like exponentials, square roots, etc. But you can also take programs and take the derivatives of programs. It's not all programs which can be taking the derivative of, but if you can, then you can actually replace some of these simpler functions with a code. So in the Jupyter notebooks, I'm not going to dive into it, but I wanted to set this up because what you see here is what we are going to do with neural networks. And we are going to calculate the derivatives by starting with the endpoint, which is this d of f, and we are going to go back till we have the derivative with respect to the initial values. Or in our case, for a neural network, it's actually the derivatives with respect to the parameters which we have. So let's now make a change. And we are going to look at a simple model. And this is going to be our first encounter with a neural network. So let's now build up our own code for a neural network. So the first step we're going to do is actually to start with a simple perceptron model with scalars only. And when we now look at the basic sketch of this, we are going to assume that there is an input x. So just a scalar input and output. There is a function which we are going to call sigma 1 here. And sigma 1 takes an argument which is going to be z1. this is going to produce an output which I will call A1. So this is the output. And I'm going to mark this one in red. So this, let me just rewrite this one as a box instead, because this is a function. So it feeds in to a function here, which I'm going to call sigma 1. So that is for this layer 1. And it has an input Z1. This feeds out an output, which then goes into a new function, which is now this traditional cost function. And this receives the output we want to reproduce. Now I'm going to mark some new variables. I'm going to have a variable y1, which is a weight, and there's going to be a b1. So one thing you could think of now is that this a1 here could be, if you now think back to what we did before with a linear model, this could be given by x times w1 plus b1. So this could be the model which we have seen before, which is just a linear polynomial. And then this b1 plays the role of the intercept, and this w1 plays the role of the how much the function raises or not. Okay? So just think of this sigma which you have there as a function. So now what we are going to do is to define this function sigma as a z1 here. This is a function of c1, where c1 is normally given by x times w1 plus a b1 here. This cost function which we have defined, if we now look back at that one, so this c is going to be a function of this a1, the output, which our model produces, and then y, which is the real output we want to reproduce. And then we have these parameters theta. And in our case, these theta are just given by two parameters, which we want to find. So as we did before, what we need now is to find dc of d omega 1 to be 0 and dc of db1 to be 0. Okay? So we have just, in a way, we have retranslated the fitting of a linear function in terms of a new function like this sigma 1. And this sigma 1 could be a sigmoid function. So an example of sigma 1, example of sigma 1, and we now just leave that undefined. This is the same as 1 divided by 1 plus e of minus c1. That's just an example function. And we are coming back to the different types of activation functions. But you see now that if you look at this simple example, even if we don't have any hidden layers, this contains the basics of a neural network. Now we don't have any hidden layers. We are going to add a hidden layer to this one. Now we have a scalar input and a scalar output. But there is nothing which hinders you to think of the polynomial which we had before. So what you could think of, instead of just this x here, you could have an x0, there could be an x1, up to some xn minus 1. And each of them would then be given by this x times w1 plus b1, which are the parameters you want to fit. So your design matrix then would just contain a row with all the n's. And if you're fitting this with a first order polynomial, your design matrix would be a matrix with two columns, one for b1 and one for w1. Does that sound clear? So I want to keep this connection with what we've done with standard neural networks. And now comes the chain rule. So when we use the chain rule, what we end up with then is the following. So we're going to get the dc of dw1, which is simply going to be given by this dc of dA1, and then dA1 of dC1, and this is the derivative of dC1 of dW1. So if you think back now, that A1 is the same as this function sigma 1 of C1, that means that this dA1 of dC1, that is simply the derivative of this function. I'm just going to write it like that. Okay? And there you see why we are going to need efficient ways to calculate the derivatives of the activation function. And when we play with different architectures of neural networks, we are going to change the activation function. So the thing we want then is to have a kind of more general code. Activation function is sigmoid, or activation function is something which is called ELO, exponential something. We have a ReLO, which is rectified linear unit, etc. There we can have a tan H. There are tons of different types of activation functions used in machine learning. So if you're going to hard code the derivatives again and again, when you change it, it's going to be going to give you a code which becomes less flexible. So this expression you see here for the final output is an expression which we will start with when we have a network with more than one output layer. That means we have a hidden layer or more than just one hidden layer. Pay attention that everything here are scalars. But then we are going to expand this to be functions of matrices or vectors or higher order tensors, just to complicate things. And then if we now look at if you go back a little bit, so we stated that this is given by x times W1 plus B1. And now you see that the dC1 of dW1 is just equal to x. If we now say that the cost function C is given by 1/2, so we have only one data point, and we put a half, so we get rid of the factor of 2 when we take the derivative. And then we just write this one as a minus y. This is again a scalar. If we calculate the derivative with respect to a, so we have a dc dA1. This is just going to be equal. We have a factor of 2. So, and then we are just going to get an A1 minus, so we have an A1 minus y multiplied with an A1. Okay? So that's going to be the derivative of that function. And you see again here that if you have a more general code which allows different types of activation functions, then with automatic differentiation, you simply say that I want to take the derivative of this cost function or that cost function, instead of having to hard code the expressions. Okay? So if I collect everything now for this specific case here, you will see now that what I end up with is sorry, not an A1 here. I did something wrong. There's not an A1, there's just an A1 minus y. Sorry for that. Then what I get then is for this dc of dW1, what I get is an A1 minus y multiplied with sigma 1 derivative and multiplied with x. If I take dc of dB1, this is going to be equal to A1 minus y times the derivative of the cost function. And remember now that if we go back, because this expression here is given by d of the cost function of d of A1 of D of A1 of D of C1, and C1 taking the derivative with respect to B1. Now, this quantity here is just equal to 1. This quantity here is just this one, and this quantity here is just that one. So it's common then to call this parameter, and you will see that this is a labeling which we will use consistently when we set up the final algorithm for a neural network. And that means that we can write this one as a delta 1 times x. So this is one of the first exercises next week. So next week, after you have programmed the gradient descent method with and without automatic differentiation, we are going to code that equation here in order to find the parameters. And then you can compare that with a polynomial fit where you make a function which has only 2 parameters, the intercept and the derivative coefficient, or how much the function rises or decreases. Okay? So the next thing which we will do next week is actually to complicate this function with a hidden layer. And this function here, or this perceptron model, which you see, can only fit up to a linear function. And this is what the universal approximation theorem says, is that if you have a continuous function which may not be linear, then a neural network with at least one hidden layer can actually fit that function to a given error. So our next step, which is then the next exercise next week, when we have this method, actually when we have these equations here, we can then set up the gradient descents. So that means that with these expressions, then we do a gradient descent and we train the parameters. So what we will have then is that the parameter omega 1 gets updated with the previous value minus a learning rate times dc dw1. And then I have that b1 gets updated with standard gradient descent, b1 minus the same learning rate of dc of d, sorry. This is the way we train the parameters. Okay? Now you see quickly that if we have more layers, we are going to get more gradients which need to be trained. And this is the simplest possible gradient descent, which we will replace with a gradient descent with momentum, or we are going to update the learning rate using either ADA-grad or root mean square propagation or ADAM as methods. So when you write a code this week in the lab sessions for a gradient descent, then you have everything ready to implement your first perceptron model. So let's now look at a simple neural network. So we still stay with a scalar. So we have one hidden layer. But scalar output and input, x and y. So these are the inputs and the outputs. So what we are going to do now is to make a new graph, because when you make this in or represent it in a graphical way, it's often much, much easier to see the structure of the equations and the structure of the network. So now we make a hidden layer, but we are still going to have our input x. But now we have a hidden layer, which I'm just going to label with 1 again. And here, so we're going to set this up here like this. This is my hidden layer. And I'm having a function sigma 1 again, which takes an input C1. This one receives what is called a bias, and this parameter bias is often set so to hinder in case your weight, the parameter W, is close to 0, which often can stop the training. So this bias is normally offset to a non-zero number, a small number, which is meant to hinder that the training of the network stops. So we have a W1, so this is a parameter. This produces an output, which I call for A1 as before, but now this one feeds into my final output layer. So this is the hidden layer, and I'm going to call this now for my output layer. And here again, there is a new function, which I call sigma 2 of Z2. And there are weights, W2 here. There is a bias of B2. And finally, this produces now a final output, which I'm going to call A2. And this goes into the cost function, which then receives the output I want to compare with. So this is a scalar quantity. There is nothing which hinders you now to replace these with more than one node in the hidden layer. Now there's only one node here in the hidden layer. So only one node. And this Z1 is now equal to W1 times X plus B1. And this Z2 is actually given now by the output A1 times W2 plus B2. And then I have the functions sigma 2 of Z2 and sigma 1 of Z1, which need to be evaluated. So these are now the variables, which means that my theta variables, the unknown quantities, are given by W1, W2, B1, and B2. So these are the parameters which I now need to train. And that means, again, that I'm going to apply the chain rule to set up the derivatives. So I will again assume that the cost function is just the standard mean squared error. So we have now a function C, which is going to be given by A2 now, which is the output. So A2, which you have here, is the output, which I want to compare with. So I have an A2, which depends on these parameters theta, and X, obviously, which I suppress here, minus Y squared. So now I start calculating the derivatives again. So I need a dC of dW2. Since this A2 depends, A2 is a function of W2 and B2. So if I look at that derivative, what I'm going to get now is dC of dA2, dA2 of dZ2, of dC2, of dW2. And just to remind you, C2 is given by W2 times A1 plus B2. That's the way we defined it. So that means that this quantity here is just equal to A1. This quantity is, as before, now given by sigma 2 derivative. And the quantity you see here is just A2 minus Y. So that means that I get dC dW2 is equal to A2 minus Y times the derivative of sigma 2 times A1. And as before, we're going to label this as a delta 2 here. So with that, we can now actually set up the next derivatives. And you see now we have a gradient for W2. So if you think of gradient descent now, you have found the equations. So that means that the W2 parameter is now updated as a function of the learning rate, which is a parameter. This is just a plain gradient descent, like that. Then we need the next ones, and dc of B2, which is then going to be equal to dc of dA2, same as, almost the same as for W2, of dB2 here. And we know that this one is just equal to 1. So this is going to be equal to this parameter delta 2 here. And we know that C2 is equal to W2 times A1 plus B2. And then we have the update for B2. That goes like B2 minus eta of dC of dW of dB2. Sorry. So now we have the equations for updating two of the parameters. Okay. So we need to use the chain rule. So what we will find next, and this gets a little bit, how to say, not too exciting. So we have a dc, we start at the endpoint, dc of A2, d of A2, of d of Z2, and then I have a d of C2, and d of A1, and then I continue of d of A1, of d of C1, and finally I have a d of C1 of dW1. So C1 is simply given by W1 times X plus B1. So this one becomes X. This quantity, which you see here, this is nothing but the derivative of sigma 1, dc of A1 with respect to A1. So if you think of C2 here, that is given by A1 times W2 plus B2. So that means that if I take the dc with respect to A1, that is going to give me the derivative with respect to that quantity. So I have a derivative of dc2 with respect to A1 is just W2. So I know exactly what this one is like. So this becomes this not as that. Let me just correct it. dA1 of dc1. So this function is nothing but the derivative of sigma 1. This one is just W1. The quantity which we have here is the one which we had before, delta 1. And then we can do the same thing with dc of B1. And when we set everything up here, we are just going to get this one to be equal to dc dA2 over dA2 dc2 over dc2 of dA1, A1 of dc1, and then I have a dc1 with respect to dB1. And the last one is just equal to 0. So it's common then to collect all these parameters into a delta 1. So this is going to be equal delta 1 times x. And this is just going to be equal to this parameter delta 1. And then I have the update rules for W1. So I have a W1, which then needs to be updated according to its derivative of dc of dW1. And we have the same one for B1, which is B1 minus eta of dc of dB1. So now I have gradients for all these parameters. Now this can now be extended to more than just one hidden node, and we can have more output nodes if we want to. But how do we train this now? So we are going to jump into a code pretty soon, which you will find in the Jupyter notebook. So everything you see here is also in the Jupyter notebook written down. So that next week, when we meet at the lab sessions, you should have all the ingredients which are needed for you to set up the first single perceptron code and a code which is a neural network with only one scalar input. Now, the reason why we do this is that as soon as we have more than a scalar input, we need to reboot our brains and rewrite things in terms of vectors and matrices. So we find it more pedagogically correct to actually start with a scalar input and a scalar out, because then you see the basic steps. And when you have a scalar input, then you can move on to have a matrix as input or just a vector of entry point. And the examples you will find here, they do actually contain this kind of different recipes. So how do we actually train this network here? So the training consists of two parts. You initialize these variables randomly, and then you feed forward your X to produce an output. So you will have a feed forward step. Now, when you then have produced an output, then you can calculate these derivatives, this one, and you can calculate this one, and these derivatives here. So that means that you start with the cost function, and you propagate backwards and update the values for W1, W2, B1, and B2. So you start with the output. So this is this back propagation where you now see all the derivatives using the chain rule. It's nothing but the chain rule. This is called back propagation. And that is nothing but you implementing automatic differentiation in a reverse mode. Because what we do is that we start with the output we produced and calculate the derivative of C. Then we go backward and we update W2 and B2. With these values, we go back again and we update W1 and B1. That was iteration number one. Iteration two is now us doing a new feed forward. And then you continue back and forth till, for instance, your cost function here, which is the mean squared error, gets as close to zero as you want. And then you stop iterating. So one iteration is a feed forward pass and a back propagation pass. And the back propagation, the way you the gradients, is automatic differentiation in reversal. And we'll see that this is more convenient because you can have an X, which is a huge matrix, whereas the output can just be one variable. So you could have one function value, like you had with the Franke function. You could have a 10-dimensional function, so you could have 10 values and just one output. And then you repeat this. So with the Franke function, you had 2 dimensions, so you would have 2 variables in, which produce one output. But then you train it on many outputs and many inputs. So that means that the complexity of the input and the outputs become more and more complex. And then we have to reboot our minds and simply rethink in terms of matrices and vectors. The way we store the data, the way we store the derivatives, etc., etc. But it's instructive to start with scalars in and scalars out, and only one hidden node. So let's go back to the Jupyter notebook and look at that one now for the rest of the day. So let's now go here. Let me go back to the screens. And this is the last thing we're going to do today. So if you now scroll down, you will recognize the same things which we went through on the whiteboard. And if you now look at the first example, this is the first example you saw, but let's look at the case with a simple neural network with one hidden layer. So this is exactly the example which we did now. So how do we implement this numerically? So here you will find the different derivatives. And I invite you just to control that I have written things correctly. So what you see is that the derivatives of the activation functions play a central role, because they are here. If they vanish, the training may stop. And this is normally called the vanishing gradient problem, which has been a serious problem and is still a serious problem in training of neural networks. The same if the gradients explode, which is called the exploding gradient problem. So these are problems which we need to keep in our back burner. But let's now look at the equations which we need to implement. So here is the algorithms which we get, and they're simply given by this parameter delta I mentioned, times the previous value here of the output. So when you look at the code example, you will see here that what I have done is actually to prepare it for more complex input. Now, the input is a scalar and the output is a scalar. But you will see that I'm setting this up as matrices and vectors so that you can reuse it for more complex cases. And here I have a feed forward pass. And I am later, if you just scroll down, so I'm using the sigmoid as activation function. So this is my first output. Now the first input to the sigmoid function. And you see I have a matmul with X and the weights plus the bias. And now these are all quantities here, all scalars. And then I have some weighted sum of inputs to the output layer, which now gives me Z2 and A2 here. And if you scroll down a little bit, you will now see that I defined the neural network only scalars. So I have only one feature, I have only one hidden neuron and one output. And then I initialize the network by some random numbers. And that's pretty common to use a normal distribution as a function of number of features and hidden neurons. And now I have only one W1, but it could be a vector. And same with the bias one and the weights and the bias in the output lane. So these are now my 4 parameters, which we had on the whiteboard. This is the way I would initialize things. And if you now look at the back propagation part, I calculate first the forward propagation, and that gives me the outputs A1 and A2. Then I set there up this parameter delta 2 from the equations. I have a cost function, which is given by the mean squared error. But since I only have one data point, I don't divide by n, because I have only one data point. I calculate this delta 1 according to the equation you saw. So for next week, when we meet at the lab, please go through these equations and see that you agree with them, okay? And then I calculate the output, weights and gradient. So this is the gradient. And what I do next, so this function returns the gradients for the output weights, the output bias, the hidden weights, and the hidden bias according to these equations, which you see up here. So these are the equations which we're coding. And then if we do this, the training part is now included here. And this is as stupid as possible gradient descent. There is no exit criterion. I put up 50 iterations and I simply update the parameters. So I do 50 feed forward and back propagation. Nothing intelligent here, right? This just reflects my brain. As simple as possible. But now you see that with this function here, which is just 2x squared plus 5x, the first guess gives me a pretty bad mean squared error. So this is the mean squared error. This is not very impressive. So it means that my random weights and biases actually didn't give me a very good starting point. But then if you scroll down here, you will see that after 50 iteration, my mean squared error is 10 to the minus 7, which is pretty good. So with 50 iterations back and forth, I have now trained a network. Obviously, in this case, I have a learning rate, which I have tuned. You can see now if I change this learning rate, suppose I put it to 001 and rerun it, you will now see that after 50 iterations, my mean squared error is 1100. So the learning rate becomes a very important parameter. So I'm going to sneak in 1 or 2 more minutes because I want to link this with the exercises this week. So you writing a gradient descent solver where you play around with different ways of updating the learning rate is going to be an important part of project number 2 because you will have to implement it. There's no way. So finding a way to optimize learning rate becomes essential. And that means also that you have to go beyond the simple case here. So the first exercise next week is to try to increase the amount of input and data points and try also to perform calculations for more values of the learning rate. And then change these activation functions with which are hard-coded here, and also the cost function with automatic differentiation. So that's going to be another part of the exercises next week, where you then can also bring in what you do this week. And everything you do now in these exercises is something you will reuse fully in the project, as you did in the previous case here. And then if you scroll down here, you will find a case with 2 hidden layers. And this is where we will start next week discussing. And you can find the expression because now we have to rewrite everything as matrices and vectors. And we need to look at the expressions for the derivatives. And when we have that, then we can move on to more than just 1 hidden layer with 2 nodes. We can go over to a general neural network. And this exercise 2 is also an exercise which we will look at next week. So next week, we are going to set up the final equations for the backpropagation algorithm for a general neural network. But take a look at these simple cases. One, just scalar input and output. And then it gets changed to have 2 hidden nodes. And if you've seen that example before this exercise, if you understand that one, then you have the basics of a neural network. So I recommend going through these steps because sometimes we can easily get lost in going directly to the full equations, because when we go directly to the full equations, we have to be careful with how we organize the matrices which contain derivatives and the data. So it's easier to start with scalar inputs and outputs and scalar nodes. So the hidden layer has only 1 node, and then increase to 2 inputs, 2 nodes, and 1 output, and then gradually build up a neural network code. I hope you see the tasks. So next week, we will then look at the final backpropagation algorithm for a general neural network and go through examples on how we can actually use that and set up our own code for a neural network. Okay, guys, best wishes with the finalization of Project 1. You are my heroes, guys. I'm impressed by what you guys have been doing.